Evet arkadaşlar, geliyor mu sesim? Okey. Sesim geliyor, tamam. Sorusu olan var mı? Ekranı paylaşıyor muyum? Ekran görüntüm de geliyor değil mi arkadaşlar? Ekranı da görüyorsunuz. Yes. Okay. Let's continue. Okay, so this was a non-example. Should we verify all the 8 properties? There's a short way out. Yes, there's a short way out. You will see it in the next section. But if even one of the properties is not satisfied, then it's not a vector space for sure, because vector space means all the properties must be satisfied. But there's an easier way in some cases, okay? Let's look at another non-example. So this is a example. This is not an example of a vector space. Okay, so now in this case we're taking V to be the set of all ordered triples x, y, z with these operations. So now we define O plus, so it takes, it is defined like this, and O dot is defined in the usual way. So let's check whether this is a vector space or it's not a vector space. You see, so the only thing here is, so this x does not enter the picture here, okay? So the other entries are added in the usual way, but the first entry, you see, it only takes the information from the second entry. So the information from the first entry is lost. So whatever this x is, the result will not change, okay? Shall I give an example for you? For example, 1 plus 2 plus 3, O plus 5, 0, 1. What is the result? So if you look at the result, for the first component, only this number enters the picture. So it is 5. And the others are added in the usual way, 2 plus 0 and 3 plus 1. So this is 5, 2, and 4. Okay? Okay, so let's talk about the properties. So the first property was, is U O plus V the same as V O plus U? This is the question. What do you think? No, right? It's the answer is no, right? Because if we take U to be X, Y, Z and V to be X prime, Y prime, and Z prime, and if I O plus them, so we know that this is X prime, Y plus Y prime, Z plus Z prime. What about the other way? So if we change the direction and add them, what do we see? Now this time this is X, X. Again, the other entries are same, Y plus Y prime, Z plus Z prime, okay? So these are not same, not equal, unless X and X prime are not equal, okay? In general, this does not hold for all vectors. That's the important thing. So let's look at the, let's look at this one. So if I change the order, you see I will get a different result, right? So if I O plus this 5, 0, 1, O plus 1, 2, 3, then the result is now 1, 2, and 4. You see, these two are not equal. These two are not equal. And we say the first condition is satisfied if it holds for every possible vectors. Okay. Now we see that the first property is not satisfied. We can check the other properties. Okay, in this case, it's interesting that the second property is, for example, satisfied. Okay, so the parentheses will not matter for this operation, for this vector operation, vector addition. The x is different, yes. So the parentheses will not matter, okay? So what do I mean by that? So if you look at this, let's call it x double prime, y double prime, and z double prime. So if I make it like this, this is equal. You can check that this is the same as x, y, z all plus x prime, y prime. No, the parentheses will matter, right? Wait a second. Maybe I said something wrong. Let's check this. So it's sometimes really confusing. Okay, let's check this. So let's only look at the first component. What is the first component of this operation? What is the first component? Because the only first component will matter. So x prime o plus x double prime will give me second component, x double prime, and x o plus x double prime will give me x double prime. So this is really x double prime, and the other entries are not important because they will not matter. What about this operation? So from here, if you look at it, this will give me x prime something o plus x double prime something. What is the result? It's again same, right? So yeah, for this one, the parentheses will not matter. So this associative property is satisfied. So it was, I think, property number 2. So this is property number 1. This is property number 2. So property number 2 is satisfied. Again, it turns out that there is no, I think there is no zero element, right? So can we find a zero element for this operation? Is there a number, fixed number, which gives, so there is no zero element. So there is 0 from one side, but there is not 0 from other side. So so since this condition is not satisfied, we will not be able to find a zero element. Okay. For example, let's see. So let's try to find a zero element. Let's write x, y, z here. Such that this O plus is really 1, 2, 3. Okay, so this is the zero vector. I want this to be the zero vector. Now, what is x, y? What should be x, y, z? So it's obvious that y should be 0, and z also has to be 0, right? Because if I add them, now for this example, so what should x be to give me this number? Yes, Kramer, you're right. This should be 1 because this strange operation takes only into consideration this x prime. So 1, 2, 3, O plus 1, 0, 0 is 1, 2, 3. Does this mean we found the zero vector? Not really, because this should be same for so if I take other vectors, this should again give me, so this should be also 2, 2, 3. So zero vector means it's a fixed vector, which satisfies this property for all vectors. But this is not true. This is not true. Okay. So there is no zero vector for this example. So the property number 3 is also not satisfied. And once property number 3 is not satisfied, property number 4 is about the negative of an element. And property number 4 really requires property number 3. So if property number 3 is not satisfied, property number 4 will not be satisfied. Okay. And you can check that property number 6 is also not satisfied. Okay, let's look at last final example. Okay, this time we have the set of all integers. Okay, be careful about this thing. Integers, tam sayılar. So this O plus is ordinary addition and O dot is the ordinary multiplication. Here, V is not, let's say, a real vector space. Okay, V is not a real vector space. Why? Because scalars are real numbers. Okay, and if I multiply, so I want this operation to be well defined. So I want this to be, I want this operation to so this should be in V for all. So this symbol means for all, C in scalars, and for all U in V. Okay, what is V now? V, let's go back again. V is the set of all integers. Now we know that this O dot is the ordinary multiplication, the multiplication we learned in elementary school. So you see that if I multiply an integer by an arbitrary real number, the result will not be an integer. So this operation, the result of this operation is usually not in V in general, which means that this set is not a real vector space. Okay. So the property B, so what is B? So there's no B here. I should fix those things. So B is, let's go back. Yeah, let's stop here. So what B is this second property. Maybe I should write B and A here. So there's this operation. So the result of scalar product should be still in V is not satisfied. Okay, guys, I hope you understand this concept. Let's look at the one last thing from this section, and then we are done with this section. So here is a theorem about, so these are not axioms. So we have seen the axioms of being a vector space. Those 8 properties are being axioms. And these can be deduced from the axioms. So they are result of the axioms. Okay, what are they? So if I multiply any vector with the 0 number, I get the 0 vector. Okay, so you can show this using the axioms. I think we have proof for this one. And if you take the scalar product of, what is this thing? I think this should be bold O. Okay, so because I'm taking the scalar product of, I'm taking the scalar product with vectors, okay, that's important. So C times the 0 vector is the 0 vector for any scalar. So this is not an axiom, but this is the result of the axiom, okay? And we know that they hold for the usual vectors as well. And so if I take this scalar product and the result is the 0 vector, then it turns out that either C is the 0 scalar or u is the zero vector. And finally, the additive inverse of u, the vector u, is really -1 scalar product the vector u. Okay, these are all like properties that you already know for general vectors, and they hold for an arbitrary real vector space. Okay, so let me just do it for let's look at the proof of the first one. The others are similar. Okay, so we have to show that zero scalar product any vector is the zero vector. How can we show this using the axioms of being a vector space? Let's look at it. So we start with the left-hand side, and we know that the number 0 can be written as 0 plus 0. So it is the only number which is twice itself, right? 0 is twice of itself. So it's the same expression now, but now we talked about some distributive property of scalar products, okay? And one of them was this. Oops, I made another typo here. This should be O plus, okay? There is no plus right now because this is a general vector space. Okay, now I get this because of the distributive property. Now you see 0, you see in the left-hand side, I have 0 O dot U equals 0 O dot U plus O plus 0 O dot U. So something in the left-hand side is equal to that something plus the same thing. Okay, now let's subtract this vector from both sides. If I do that, one of them will get away and we will get the zero vector here. So we have shown this. Okay, so the proof is not too much important. So all of these properties can be easily proven. Okay. Let me know if you have any questions. I'm sorry about the typos. I will correct them in the lecture notes. So I'm putting these lecture notes also to our website. Okay, you can check it from there. And also we're putting the videos onto like Uzem website. You can find the lectures from there. Let's pause for a minute and let's see if you have questions. Do we need a zero vector for all each vectors? So zero vector is a unique vector which satisfies this property for every u. So let me write it in bold. So zero vector means, so this should hold for not just one u, but every u, every possible u in that vector space, okay? So this is a fixed vector such that its addition with any vector gives the vector itself. I hope this answers your question. I get all the rules, but it really is an abstract subject, as you said. Yes, it's an abstract subject, and we will see that the solution of linear systems really fit into this structure. So anything we say about this general structure, about these vector spaces, will hold for the solutions of these linear spaces, these linear solutions of these linear equations. So they really fit into this frame very well, okay? That's why we teach this in linear algebra course. Is there a zero vector? What do you mean, Gilfoyle? Is there a zero vector? I mean, zero vector depends on your definition. So for each vector space, the zero vector will be different, okay? For example, for the vector space of matrices, the zero vector will be a matrix. For the zero vector of the polynomial space will be the zero polynomial, things like that. So for each vector space, there will be a zero vector, and the meaning of vector will also change depending on which vector space you are. Yes, ask me if you have questions. And if I can't answer them, let me know again. So I will try to answer again. Okay, guys, let's continue then. Okay, so some exercises for you. Now, next section, 4.3. So this section is about subspaces. Okay, let's first define what is subspaces. Now, we have a vector space. So whenever I say vector space, okay, you should understand real vector space. So in this course, vector space and real vector space means the same thing, because in all the examples we will see the scalars will be real numbers, okay? We will not talk about different scalars. So there are, as I said, there are different scalars, but we are not interested in them in this class. Okay, so now we take a non-empty subset. You know what a subset is? Subset is a sub-collection of elements, right? Subset. So V is a vector space and W is a subset. For now, it's just a subset. If W is itself a vector space with the same operations that are in V, then we call this W as a subspace. So we're taking a big set V, and we're having a small subset of it, which is W. If W itself is a vector space, then we call that W a subspace, okay? So a subspace is really a vector space of larger vector space. That's what it is. Now here comes an important theorem. Okay, so important theorem is this. Okay, we have a vector space with these operations and W is a subset. Then W is a subspace of V if and only if the following two conditions are held. A, if U and V are any vectors, then their sum is in W. B, if C is any scalar and U is any vector in W, then C times U is in W. Okay, now I don't use O plus and O dot. Whenever I said it like a plus, I mean O plus, and this means O dot. Okay, so what is the importance of this theorem? Now the importance of this theorem is this. Okay, so we're claiming that W is a subspace. Now subspace really means a vector space, right? W vectors, yeah, to be a subspace, you have to be a vector space. Now to be a vector space, you have to satisfy all those properties, 8 properties and properties A and B. So there are really like 10 properties. So what this theorem says is you really need to check that only property A and property B, which are the closed, being closed operations. So let's go back to our definition slide. Okay, so to be a subspace, only property A, so this line, and property B, this line should be satisfied. You don't need to really check all those properties. Okay, so if these two properties are checked, then the rest comes naturally, being a subspace. Okay, this is only true for subspaces. So this is in a sense an answer to what Nesrin asked last time about whether there's an easier way. So yeah, this is kind of an easier way for some cases. Okay, in some cases we can easily see whether given set is a vector space. Okay, so the proof is very easy for this one because we know that all the properties, the other properties are already satisfied, being V being a vector space, because V being a vector space means all the other properties will hold in the larger space. So once they are holding in the larger space, they automatically will hold for in the smaller space. The only things that we have to check is whether if you take any two vectors, their sum is still in the set, that small set, and this property. So C times U should be in that small set. So this is a very, very important theorem. We will see some examples of it in the next slides. Okay. Very useful theorem, very important theorem. So you should know this theorem. Okay, now this is like a theorem and an example. So regardless of which vector space you are working, that vector space has at least two subspaces. One is itself. So every vector space is a subspace of itself. So this is very trivial. And the next subspace, next trivial subspace is the subspace zero subspace. So we know that every vector space has a zero, right? Zero vector. So if I only look at the, if I take W to be the zero vector, then this W vector will satisfy these two properties, right? Why? Because so I should write zero vector here. So if I take two elements from W, which I can only take as zero vector, their sum is still in W. And if I take any real number and I multiply it with any number in W, which means, okay, so this is really O plus. If I multiply it with any vector, which means there's only one vector here, the result still is in W. So the only element consisting of the zero vector is still a subspace. So this is a special name, zero subspace. Okay, guys. So what have we seen in this theorem example? We have seen that every vector space always has at least two subspaces. One is in itself. Okay, this is trivial. The other is the subspace, the zero subspace. Okay, the zero subspace consists of only one single element, which is the zero vector. Okay, now let's look at some examples of subspaces. Okay, now in the last section, we have seen that P2, the set of all polynomials of degree less than or equal to 2, this was a vector space. We talked about this. And we have also talked about a vector space of all polynomials, okay, regardless of the degree. This is also a vector space. And the thing is, P2 is a subset of P, okay? Subset of P. So the set of all polynomials of degree less than or equal to 2 is a subset of the set of all polynomials. And they have the same operations, same addition operation and same scalar product operation. So this P2 is really a subspace of P. In a way, we can think like this. So if we can show that, if we have shown that P is a vector space, then to show P2 is a vector space, we only need to check two properties, not 10 properties. Property A and property A and property B. Now, what was property A? Property A was this. If you take two vectors from that set, their vector addition should be in that set. Okay, so if we take two vectors, now our vectors are polynomials of degree less than or equal to 2. So if I add them, we know that for polynomials, the result will, so if you add two polynomials, then the degree will not increase, right? If you add two polynomials of degree less than or equal to 2, then their sum is also a polynomial whose degree must be less than or equal to 2. Okay, it can be less than also. Okay, so we know how to add this, right? So this is a plus d plus, so you see the degree doesn't change. I mean, it doesn't increase. It can change, but doesn't increase. C plus fx squared. So this is property number A, so it is satisfied. And we also have to show that property number B is satisfied, which is C times A plus bx plus, let's write dx squared. So this should be, so what is this? This is AC plus bcx plus dcx squared, okay? So the result is again a polynomial of degree less than or equal to 2. So here we check that the sum of two polynomials of degree less than or equal to 2 is a polynomial of degree less than or equal to 2. And the scalar product of a scalar with a polynomial of less than or equal to 2 is a polynomial of less than or equal to 2. Okay. So this somehow reduces the number of computations that you have to do. So you don't need to check all the properties to show that P2 is a vector space. So once you know that P is a vector space, you can show that P2 is a vector space by only checking these two properties. Any questions? Okay, let's look at the next example. This is a non-example, okay? So this is not an example of a subspace. So here, let's take W to be a set of all polynomials with degree exactly 2, okay? So not less than or equal to 2, but exactly 2. So is this a vector space? Is this a vector space with the usual polynomial addition and scalar product? Is this a vector space? So the answer is no. Why no? Because if I add this polynomial to this polynomial, then you see their sum is, what is their sum? Their sum is x plus 1, right? So this is not a polynomial of exactly degree 2. So this is, degree of this polynomial is 1. So sum of two polynomials of degree 2 can make a polynomial of degree 1. Okay, so this set is not closed under vector addition. So this is not a vector space. Questions? No questions? Okay, let's talk about few examples and then we will finish. Okay, I'm asking you this. So we're talking about r square, okay, r square. So this is vectors in the plane, so their components are a, b, or x, y. So we take the usual vector addition, adding vectors in the usual way, and scalar multiplication. The question is this: is this set the set of all vectors of the form xy, where the first component is greater than or equal to a subspace? So what does this mean? This means please check those two properties. So check whether they satisfy these two properties. So is it true that sum of two such elements is still such an element? And B, is it true that if I take such an element and multiply it with a scalar, then the result is still such an element? Okay, so let me write it here. So example A. Check so let's call this set B, W. Okay, let's call this set W. C can be any real number. Yes, C can be any real number. You're right. So that's important. You're right. So if this is in W and if this is in W, is it also true that their sum is in W? What does being in W means? Being in W means the first component is greater than or equal to 0. Okay, that's what it means to be in W. So this means x is greater than or equal to 0 and x prime is greater than or equal to 0. So if I add them, you see their sum is what? Their sum is x plus x prime, y plus y prime. Okay, second coordinate has no importance. What is important here is the first coordinate. Is this sum, is this first coordinate satisfy this property being greater than 0, greater or equal to than 0? And the answer is yes. Right? Why? Because if I add two numbers which are greater than or equal to 0, then their sum is also greater than or equal to 0. So this is certainly in W. So the first property is satisfied. Property A is satisfied. A is true. But the second property, you're right, Nesrin. Yeah, second properties will not be satisfied. Let's see. So let's see. Let's look at property. So second property says if I multiply any vector by a scalar, then the result should be in W. So if this is in W and C is any scalar, okay, if C is a real number and this is in W, then the result should be in W. This should hold for every C and every X and Y. This should for all C and all X, Y. But you see, this will not be satisfied if C is a negative number, right? Because let me give an example. So 1 and 2 is in W. Why? Because the first component is greater than or equal to 0. But minus 1 times 1, 2 is not in W. Because now the first component is minus 1. And if the first component is not greater than or equal to 0, then it's not in W. So this is not in W. So property number B is not satisfied for every possible C and every possible XY. Okay, so B is not satisfied. which means the given set is not a vector space and it's not a subspace. Okay, so this set is not a subspace. Let us see geometrically what this set is. So it's x coordinate, so this is the set where the x coordinate is greater than or equal to 0. So this is not a this is the set. So this is not a vector space. Not a vector space. Okay, let's look at the second part of this problem and tell me what you think about this one. Whether this is a subspace or not a subspace. Here, we should really write it like 0 and y, okay? So the all vectors of the form 0, y. So the first component of the vector is fixed. So is this a vector space? Okay, answers, please. What do you think? Is this a vector space or no? Okay, yes. So we get two yes answers. So the result, the answer is yes. So this is really a subspace of R2. So if you take two such vectors whose first component is 0, and if you add them, then the resulting vector will also have the first component 0. So the condition is satisfied. So for vector addition, right? So sum of two such vectors is such a vector. And if you multiply any such vector whose first component is 0 with a scalar, the result will still have the first component 0. Okay, so second condition is also satisfied. So this is a subspace. Okay, so you can see that I don't want to write anything. You can see that this is a subspace. Okay, this is a subspace. So for part number B, so what does x equals 0 mean? X equals 0 mean really this line, right? So this is the line where x is 0. So this line is a vector space, but you see this region is not a vector space geometrically. So we will talk about like the picture of vector spaces. So in Rn, so like lines will be vectors. Lines passing from the origin will be vector spaces, and the planes will be planes passing from the origin will be vector spaces. But such regions will not be vector spaces. So for example, such a region cannot be a vector space in R2, okay? Because if you take two vectors here, and if you add them, the result will move out of this bounded region. This is only like a picture idea, okay? So for example, this will not be a vector space, because if you take a vector and if you multiply it with 10, it will go like this. It will get out of this region, okay? So bounded regions cannot be vector spaces. Okay, I hope you get the idea a little bit. I think we can stop here now. So this is the last thing we did. So next time we'll continue from here. Please try to go over these things again before tomorrow's class, okay? Otherwise, you may feel lost. Please try to repeat them. And yes, tomorrow, if you have questions, we can start with your questions about these things. I am lost already. Attila, it's not too difficult. Please try to go over it. Listen to this lecture again, okay? I will put it immediately after the class. Try to listen to it again. I don't want you to be lost, okay? It's not super difficult, but it's like an abstract idea. Okay, guys, so yeah, I think we can finish now. If you have questions, please ask now, or if you don't have questions, you can leave the meeting. Hepinize görüşmek dileğiyle diyorum arkadaşlar. Ben de bu arada şu typoları yazayım. Bitti. Şimdi bitti. Yo, dur bakayım, şeyi kapatmadım. Bir saniye.